Right. Hi, everyone. For those of you who don't know me, my name is Craig Sheridan. I'm a professor at Wits University, and I'm going to host today. So I've specifically asked Sasha if she'll give me the screen for a minute. And the reason I want to do that is I'm going to be showing you some really nice scenery, and it's a beautiful sunny day, and it looks wonderful. The reason I'm trying to show you this is to make you jealous and register for the conference that we're holding in April next year. So that's not next year, this year. Sorry, someone just reminded me, it's April this year. So what you need to do is you need to go online and go to the IIES website and please register for the conference and the workshop. And then you too can enjoy scenery similar to this. In fact, it's slightly nicer where the conference and that will be held. So to start then, what I'm going to do is I'm going to read the citation for Tamlyn Naidu. It gives me a lot of pleasure to introduce Tamlyn Naidu. I asked her for her précis this morning, and I'm actually going to read it verbatim because it's probably correct. It says, Tamlyn Naidu is a chemical engineer and was one of my favorite students. There we go. Throughout her career, she has been dedicated to wastewater treatment with a strong focus on the valorization of or value derivation from acid mine drainage. Her master's and PhD research centered on innovative approaches to AMD treatment, exploring how waste streams from different industries can be transformed into valuable resources. Beyond academia, she has worked in industry, designing and consulting on water treatment plants across sectors, including abattoirs, sewage treatment works, the food and beverage industry, and mining operations. Sasha is now a postdoctoral researcher at the University of Copenhagen, working on a Danish Ministry of Foreign Affairs project tackling the critical issue of acid mine drainage. And today she will be sharing key insights from both her research and real-world case studies, showing some possibilities of how we can transition from a linear economy in the water sector to a more sustainable circular model. So with that, I would like to hand over to Sasha, and yeah, let's hear what she says. Thanks.
Thanks, Craig.
Yes, we can hear you. Perfect. Go for it.
Great. So when we talk about environmental issues and sustainability, the headlines are almost always the same. Here are some examples, and these are not hypothetical examples. These are actual news stories from the past week from the BBC and from the United Nations. And it is always, a corporation facing massive fines for pollution, another contaminated river, wildlife suffering due to industrial waste. And while they are undoubtedly real and pressing stories, they do contribute to a narrative that is overwhelmingly negative. We hear a lot about pollution, waste, and depletion, about how things are getting worse, how resources are running out, and how human activity is accelerating environmental decline. And the data also seems to support that story. According to the Circularity Gap report from 2024, which was compiled by the World Bank, the Circle Economy Foundation, and Deloitte, despite discussions about circularity having increased by 3, real action is lagging, and in some cases, it's getting worse. Global circularity has actually decreased from 9.1% in 2019 to just 7.2% in 2024. And in that same period, in those 5 years, we consumed 500 billion tons of material. And that's roughly, apparently, equivalent to what was consumed in entirety in the 20th century. So yes, the numbers do paint a stark picture. And this isn't just a feeling, it is a measurable reality. But that brings us to an important question. How do we move forward? Do we continue seeing these numbers as proof of inevitable decline, or do we take them as a challenge to rethink our approach? Now let's look at this glass of water. A pessimist would say it's half empty. An optimist would say it's half full. But in the world of sustainability, emotions won't solve this problem. only solutions will. And so I would say a circular economist would look at this glass, and instead of classifying it negatively or positively, they would ask, how do we reuse this water? How do we repurpose the glass? And can we extract and market any valuable minerals that are left in it or afterwards? So in other words, instead of framing the problem as loss, we frame it as an opportunity. And that's what I'd like to try to do today. Yes, the challenges are real. Yes, the data shows that we're not yet moving fast enough. But rather than focusing on why circularity is failing, I thought I'd try and highlight why and where it is succeeding, because solutions do exist, and they are already being implemented across quite a few different industries. So the title of my talk today is From Waste to Work, Transforming the Linear Economy to a Circular Model. And to illustrate how this transformation is happening, I'm going to take you through 4 different industries or 4 different operations at different sites where water is being used and or treated and or managed in some way. The first one is going to be a beef abattoir or a slaughterhouse, a fast food chain, a steel mill, and a mine or mining operations in general, overall mining. And each of these industries once operated on a highly linear model where waste was an inevitable byproduct of production. But through innovation, necessity in most cases, and in almost all these cases, economic incentives, they have started moving towards circular models where waste is not an end product, but a resource used for something else. Importantly, what I hope to show with these case studies is that circularity is not just about what happens inside one company or one industry, but how industries can interact with each other to benefit one another. Because true sustainability is not just about reducing waste, it's about rethinking an entire system. So I'll be drawing from my own experience today in industry and also some research from my PhD. So bear with me if I've sensationalized a bit, but I will let you know when and where I have done this. And also bear with me in terms of pictures. These were all NDA'd sites, so they've been slightly altered so you can't tell where these plants are or which sites they are. And first, very quickly, a recap of what the linear economy is or was. So for decades, industries operated on this linear economic model. Take, make, use it, get some use out of it at least, dispose of it, and then to waste. And this, of course, made sense historically. It was efficient, it supported mass production, and it drove economic growth. But now we've hit a wall. Waste is piling up, wastewater or polluted water is becoming saturated with elements or constituents that we actually see there is value in, and water scarcity is intensifying. So not treating water properly before discharges is no longer doable. And regulations are tightening, and companies are slowly realizing that waste is just a resource that is in the wrong place, that is being thrown away. And in some cases, they are being fined heavily for disposing of these waste streams when in fact they can be using them for a benefit of some kind. The circular economy, on the other hand, challenges this linear model by trying to turn waste into a valuable resource. And interestingly, in the work that I'll show today, I found that these companies, these were the companies that we're often seeing as polluters, you know, the villains of environmental narratives. But in fact, they're actually some of the biggest drivers of circularity. So to start off, we will look at case study 1, and this is the slaughterhouse. And this is the first site that I ever worked in or at a slaughterhouse, and it was a massive awakening regarding what wastewater and treating wastewater actually entails. The waste from an abattoir is, in my opinion, 10 times worse than a sewage treatment plant. Blood, fats, stomach content, and more, all washing down the drain. So this short video is from the site before any changes were implemented, and all the waste here that you see flowing out of that pipe, it all led into one outlet sump. So it was as linear as it gets in terms of process model. And we'll start with what the situation looked like before circular economy principles were applied. So a slaughterhouse by its nature produces a significant amount of waste, organic waste, both in liquid and solid form. And there are various points in the process where waste is generated. So you have cattle holding areas where manure gets washed into the wastewater drain. During slaughtering, blood, which is actually an incredibly nutrient-rich material, is flushed away. The offal processing stage, where the stomach, the bladder, and other organs are cleaned, contributes even more organic waste into the wastewater system. And of course, fat removal, which adds a significant amount of oils. We call it FOGs, fats, oil, and greases, which complicates wastewater treatment processes quite a lot. So this was a textbook linear economy: consume, use, and discard. And the wastewater generated from this process carries a high organic load. So that means high levels of COD and BOD, which is chemical and biological oxygen demand, and the FOGs, the oils, and the greases. And all of these things contribute to severe environmental pollution. And what's more, this slaughterhouse was facing pressure from regulators because their wastewater was overburdening municipal treatment facilities in the area, which were already struggling. So they were at risk of fines or even closure. And even if they did sort the outlet out, so they treated it in some way, they would still then be at risk of not getting any water from the municipality in general, because water supply in the area was scarce as it was, even without improperly functioning municipal works. So this is what we started at. This is where the shift from a linear to a circular approach began. They first had to rethink their process. And interestingly, I'm not sure if it's a good or bad thing, but this was done not necessarily out of a passion for sustainability, but because of economic and regulatory pressure. And a basic breakdown of what the changes implemented were: the first was blood recovery. So one of the largest contributors to their wastewater load was blood. And this isn't just any type of waste. It's high in protein and incredibly valuable. They were already processing this, but due to a non-optimized separation process at the beginning, they were losing about 20% of their potential product to waste. So instead of letting the excess blood wash away, we implemented a collection and separation system to recover as much blood as possible. And this wasn't a high-end technical solution at all. It was just essentially building two pipes instead of one and changing when they did a wash cycle. And they recovered this blood, which was then processed into blood meal. And this is a key ingredient in animal feed and pet food, some premium pet food. In fact, I remember when working on this project, it was during a period in South Africa where we had a shortage of the royal canine or royal canine, I don't know how you pronounce it, pet food. And I just thought to myself, we're literally washing half of this valuable ingredient down the drain. And they recovered it, and this change wasn't about environmental responsibility, it was about profitability. By maximizing their recovery, they turned what was once a pollutant into extra product with market value. The second item that they tackled was tallow production. So the same logic did apply to this, fat recovery, basically. Before, there was very poor separation processes, meaning that a significant portion of the tallow, which again is a valuable byproduct, it's used in soap, in biofuels, and in cosmetics sometimes, this was lost in the wastewater stream. And by introducing improved separation techniques, they were able to capture more tallow, reducing the FOGs, the fats and oils and greases, and reducing the burden on the wastewater, which reduced the amount of treatment that they would need then before outlet. And again, there was no chemical treatment here. This was a simple change in management or change in operational procedure where they changed when they released the wastewater and when they skimmed the surface of the sump to remove the fats. And here you can see the fats at the surface. Once they were removed, they were put into these tallow tanks. And again, the motivation here was profit, but the unintended benefit was less pollution. Lastly, it was biogas energy, which is something that we got from this process. And this is more of a technical solution that we did need some involved thinking and engineering design for. The slaughterhouse's solid waste, which included undigested feed, organic matter, and fat residues, because there are still some smaller particles that will not get removed just from simple physical solid separation. This material is ideal for anaerobic digestion. And this is a process that breaks down organic waste using microorganisms to produce biogas, methane generally. But to make this work, solid liquid separation was key. We'd had to separate those solids from the liquid in order to use it as a substrate. So we installed a clarifier to remove the heavier solids. And there were a lot of solids here, so we did need two processes. So we also did, for the finer solids, a dissolved air flotation unit. This was introduced, and this basically uses tiny air bubbles, which are dissolved in the liquid to lift any remaining solids to the surface for easy removal. And unfortunately here we had to use a chemical input. So this introduced an open loop, there was an open loop here because we have now an extra addition into this system. We have to add to the process. However, the setup did minimize chemical use because we had two physical processes instead of one, and it kept the costs down, which ensured very low amounts of chemicals were used and that the bacteria, or the microbes rather, in the digester weren't inhibited by excessive additives in the sludge. And the result here was a renewable energy source, which was generated on site, which reduced their reliance on external power. And they did already do this because they had manure and paunch that was coming out of the system. But the additional sludge that now was generated and used, they had 6 digesters on site and they added another 6 to this. And this was actually just as the system was starting up. So at this time, it could be more, I'm not sure. And they also used the finer sludge to treat some of the soil on their surrounding properties. And they did have to use an additive here as well in order to make it suitable for soil amendments. And the additive that they used, they were involved in a lot of experimental techniques at the time. And one of the ones that they used was a steel slag powder. So again, that was another open loop. Chemicals need to be added for water treatment, and another additive needed to be added to the sludge to use it for soil amendment. But after this, all of the treatment, at that stage, the water exiting the process was significantly cleaner than before. And this is just an image of before and after treatment. But of course, this wasn't potable. It still needed further treatment. However, the partially treated wastewater was now fit to be sent to municipal treatment plants. And there were even discussions at this point about installing a reverse osmosis system to fully recycle water for internal reuse. I'm not sure, but I think that the site is actually currently building this. But again, the water reuse here wasn't just a sustainability measure. It was a business strategy. Rising water tariffs and drought conditions in this area, securing a stable water supply would be a major competitive advantage. So again, not necessarily not concerned with sustainability, but the main driver here was a business strategy. However, this again was then an open loop. So we now had a stream of water that was not fully reused or returned to the system. They did use some of it for washing and processing the processes that they could use grey water for, but it was still an open loop. So a few open loops in the system now. Number one, the treatment still required chemical inputs, specifically coagulants for the solid separation. And just to give you a little bit more information, because I'll link this later on, this was iron or aluminium-based coagulant, so an iron or an aluminium sulfate or chloride. Number two, the additives that they were using for the soil, along with the sludge. This was the steel slag, and now, of course, the outlets, which was a partially cleaned water. Some of that water was not returned directly to the plant. But by this point, nearly everything that was once considered a waste had been now repurposed into a valuable product. So there was tallow, now sold as a raw material for soap and biofuels, blood meal used in animal feed and pet food, COD-rich sludge fed into an anaerobic digester for biogas energy, and partially treated sludge, which is applied to the fields around the area as a fertilizer supplement or a soil amendment. But these three open loops still remained: the chemical coagulants, the soil additive, and again, the water. So the fact that not all wastewater was fully recovered for reuse, all of this meant that the system wasn't fully circular, but it was still a significant step forward. And the drivers for circularity here, as I've mentioned a couple times now, primarily it was profit. Recovering valuable byproducts meant higher revenue and lower losses. Secondarily, I would say it was regulatory pressure. They needed to comply with discharge limits to avoid fines. And the last driver actually was sustainability, which is interesting. And I would argue later on that this is a good thing, because it means that we can drive circularity not just by trying to leverage people's humanitarian side. So by reducing waste and improving water efficiency, they were able to cut costs without costly technical interventions and create a more sustainable solution. So while their motivations were financial, the outcome was environmental. And they were able to achieve near full circularity at the end of this transformation. However, as I mentioned, there were still some gaps, but before we close those gaps, or rather as a way to close those gaps, I'll move on to case study 2, which was on the other end of the spectrum, shifting our focus from waste treatment at an abattoir, where we are trying to process or provide meat, to water scarcity in fast food operations. So this was also in South Africa, and of course, SA is not a stranger to droughts. And during one particularly severe drought period, many businesses found themselves in a crisis mode. And I mean, this is arguable, but the food chain that we were assisting here, they argued that very few industries were hit as directly as fast food chains. Why? Because they have strict regulatory requirements. So if a store doesn't have running water, it must close until water is restored. So no water means no hygiene, no safe food preparation, and no way to actually operate safely. And for a large fast food franchise with multiple stores across the country, this was a major financial risk. Some stores remained closed for days, and this led to significant revenue losses. And the brand's governing body, the corporate board that set the operational standards for all of the stores, they recognized that this was not just a localized issue, but a network-wide crisis, and they needed a long-term water resilience plan. So before bringing us in to find a more sustainable solution, they did try some of their own solutions that they tried to implement. One of the quick fixes that they implemented was buying water from a nearby stream, which was located on a farm. And that water was then trucked into the city and stored in tanks at the restaurant. And while this did provide an immediate fix, it had two major problems. It was expensive. Small-scale water trucking is logistically inefficient and costly, and it wasn't scalable. A single water source couldn't sustain, dozens of stores, given that this area was already in a drought crisis. So clearly they needed something better. And our proposal was simple but effective. They would install water collection tanks at each stores and filter and chlorinate the collected water to make it safe for use in the store. And they would reserve potable water, so directly from the municipality, drinking quality water, for food preparation and essential processes. So when water was cut off, they could use their reserves of potable water for the main operations, and they could use the collection tanks with an additional treatment method for any other supplementary processes. And that would mean that tasks like cleaning floors, flushing toilets, and general hygiene maintenance, especially on areas outside of the kitchen, wouldn't have to rely on municipal drinking water. And this would reduce strain on both the store and the city's water supply. But where would they get this recycled grey water from? And this is when we started looking beyond the franchise and exploring the potential of inter-industry water reuse, so between different industries. And instead of trucking in raw water from a distant farm, which we didn't know what the quality of it was, and it was constantly changing, we looked at existing industrial wastewater streams that were already being treated, that we knew the constituents of, that could be reused safely, because we would know what is in it and what it is being used for. And one of the proposed sources was the abattoirs treated wastewater. And this is a perfect example of circularity in action. What was once considered wastewater from one industry could now become a resource for another. So instead of discharging its treated effluent into the environment, the abattoirs water could be repurposed for non-potable use at other outlets. Now, they didn't use this option. They instead actually used a treated water from a car manufacturer, which was much closer. But the principle still stands, that it was something that was considered a waste that was now being used as a resource in another industry. And in our last case study, we'll take a step back from both the food production and water shortages, so from the food industry in general, and shift our focus to heavy industry, specifically steel mills and mining operations. And this was primarily my PhD research. Steel mills generate slag, which is a byproduct that is rich in oxides. And while this slag has valuable applications, generally being used as a construction aggregate or as a soil amendment, because this is also one of the products that they used at the abattoir. It has one major issue when being used in construction, and that is structural instability. There are a lot of free oxides in the slag that react with water and air when it comes into contact with it, and this forms hydroxides, and a hydroxide is bigger than just a simple oxide, so it causes swelling, and this is causes volume instability, which is not something that you want in construction materials. And the traditional solution to this is to treat the slag with acid, which stabilizes it by removing these free oxides. But this brings us back to the linear economy model, because acid then now is an external input into the system, requiring transport and additional costs in order to acquire it and use it. But here's the interesting connection. Many steel mills are located in regions that also deal with another major industrial waste, acid mine drainage. AMD is an acidic waste stream that's produced from mining activities, and they contain large amounts of sulfate and iron primarily, with some other anions and cations, metal ions as well. And the treatment method for AMD traditionally, where they do treat it, is it's neutralized using lime, which leads to the precipitation of metals as oxides and hydroxides and sulfates. And it is a slightly costly process only because it now requires yet another external input, chemicals, in order to treat the stream. So instead of treating these two waste streams separately, what if we paired them together? Instead of viewing the two as separate problems, we asked the question, can one waste stream be used to neutralize the other? And the answer is yes. Slag is alkaline because it is essentially lime that has absorbed some impurities from iron ore, and it reacts with acid. And AMD is acidic. It requires neutralization. So by treating AMD with the slag, we effectively neutralize both waste streams at the same time. Neutralize the AMD, treating it to a better quality, removing a metal-rich sludge, and removing the volume instability from slag, which had free oxides present before. And the result that we get from this is a cleaner water stream, a stabilized slag product that can now be safely used in construction, and a reduction in the need for external chemical inputs, and making the process more cost-effective and circular. And this was a major breakthrough, but it still left us with one more challenge. And that was, while the solution successfully treated both slag and AMD, it left us with one final waste product, another open loop. And this was a sludge rich in iron and sulfate. And while the sludge is less hazardous than untreated AMD because we can control it better, it's still a waste product, which means the loop isn't fully closed yet. And so we started looking at other industries that iron-rich materials can be used, and that's when we saw an interesting possibility. One of the major applications of iron-based materials is in water treatment, specifically as a coagulant to treat water across industries. And it's the same in abattoir treatment. As I mentioned, they do use iron-based coagulants, and that is what they were using at the site to optimize their liquid-solid separation. So coagulants help to remove organic pollutants, like all of the organic materials, COD and BOD that we had in the abattoir waste, by destabilizing the forces in the water and making them easier to separate and flocculate and clump into a heavier solid that will drop out. So we conducted tests using this iron-rich sludge. We did have to do some prior treatment to it before using it, but we used it to check if we could drop this organic matter out. And the questions we asked were, could it be used to separate organic matter? Would it be as effective as conventional coagulants like the iron chloride or aluminium sulfate that we were getting from other companies that we were buying? And the results were highly successful. So instead of being a waste product, the iron sludge from AMD treatment was now repurposed as a coagulant. And this brings us a full circle to cleaner water and closes all of the loops in our 4 industries and 3 case studies here. So over the course of these case studies, we've seen how circularity isn't just a theoretical concept that we would like to achieve. It's already being achieved across industries. It's real, it's tangible, and it's a business strategy that works. From the abattoir transforming its waste into valuable byproducts, to the fast food franchise tackling water shortages through industrial partnerships, and then to the steel mills and mining waste combining to create a mutually beneficial solution. A few things remain clear. Circularity doesn't happen in isolation. It thrives when it aligns with economic incentives. It works best when industries collaborate rather than operate in silos. And even when loops remain open, as we've seen in these case studies, they highlight areas for further innovation and opportunity. It doesn't mean that it's a loop that now we have an opportunity to find a use for. So essentially, we need to stop looking at waste as an end product and start seeing it as a resource in transition, any waste, whether it is directly from the process or from the treatment process that you are proposing. Waste isn't waste until we actually waste it. And most importantly, I think that in these examples, something to note is that circularity isn't automatic. It has to be designed and implemented. Processes need to be changed, and we need to do multiple adaptations over time to our real world constraints. So as we move forward, the question isn't why isn't circularity working, or why is it getting worse? The question should be, where is it already working, and how can we build on that success? So the mindset that we need, not just in wastewater, but in every industry that wants to reduce waste, increase efficiency, and build a sustainable future is this. Where is it already working, and how can we build on that success? Thank you.
Thanks so much, Sasha. If I could figure out how to clap hands on the screen, I would do it. I can't see the button. So I mean, I really like your thing about waste, and it reminds me of the saying that weeds are just flowers that nobody wants. So I guess in the same way, waste is just resources that nobody wants at the moment. Yeah, and then I did have a question on a slightly technical one. At the abattoir, how much biogas did they make, and what were they actually using for? Was it just for heating or what?
Oh, I'm actually not sure. That's something that I would. Yeah. I'm not actually too sure. I think I suspect it was heating. They had it. They had all of the digesters at the edge of their property, just next to where they had like a clean area where they would package and um, cut, etc. So I assume it could have been something used in there. I'm not actually too sure what they used that for.
Okay, maybe for boiler water or something.
Yeah, probably.
Yeah.
Yeah.
Okay, thanks. So then I would like to open up the session to all of you. Do any of you have questions for Sasha? Either I haven't seen any questions in the chat box. So if you have questions, you can either raise your hand or just speak out. Great, thank you, Marilee. Please, yeah, you're on mute, so if you'll unmute yourself and go for it.
Hi, Sasha. Thank you very, very much for your talk. It was very interesting. I also did my PhD regarding metals in water, metal pollution in water in the Vaal River system. And I just wanted to ask you more or less, like, have you published your results yet for case study number 3? It would, to me, be very interesting to see the stats on the water before and after the treatment was done. And yeah, especially for something, considering that aluminium is usually very high in acid mine water.
Yes, so the findings from that study have all been published, and primarily it's the way that the acid mine drainage was treated, and how the iron and the aluminium and all the other metals were removed using the BOF slag. The work on using the sludge as a coagulant for treating organic rich wastewater, that's in the process. We've done some lab tests on that. In some cases, it's almost as effective as using a pure, like a 37% ferric chloride or ferric sulfate coagulant. But that's in the process of being published because, of course, there are other metals in the sludge. So it's not just iron and or aluminium. There are some other metals like manganese, copper. And what we ideally would like to do before using those valuable metals for just water treatment is try and extract our rare earths, our other critical raw materials first before using it to treat wastewater.
Thank you very much.
Yeah, okay. Those articles are
No,
available online.
I will definitely look for them. Thank you very much. Very interesting. Thanks.
So perhaps, Marilee, if you want, you can drop Sasha an email, and she can also share those papers with you if you're looking for them. There is an online question which says, it's from Margaret, how do we incentivize industries to link together, to work together to achieve circularity? Is a real-time waste inventory something that might be envisaged for industries?
Sure. I mean, I feel like we should open that question up to the floor. In the project that we're working on currently, absolutely, this waste inventory is something that we're trying to put together. At the moment, we're just using open source software like Google APIs because they have an extensive database of what industries are where. Because we need to link industries not only based on what they do and what waste they produce, but also their geographical region. You want to be able to repurpose waste in the same area and not have to travel thousands of kilometers or transport waste that could be used as reagent from very far away to your industry. But I would say that definitely is something that we envisage could work. The answer is I'm not sure how we would incentivize it other than showing that it can be used to generate additional profit or to lower other costs.
Sasha, I mean, if I think of that question, I think it's a little bit like trying to promote interdisciplinary research, is that you have a whole bunch of different discourses all running in parallel, and how do you get them all to talk to each other at the same time? Because kind of you need to know what's going on at each site, so you need an oversight of the whole ecosystem.
Yeah.
So maybe promoting like community meetings where community is actually the industries where people can talk about what they do and stuff could work. I don't know.
Yeah, I mean, I guess some type of easily accessible platform like that where industries in the same area meet regularly. And also, I guess it needs to be a little bit of a transparent process where industries need to be comfortable sharing what waste they are producing and what's in it and how that can be, or if we know what's in it, we know how it can be repurposed. At the moment, it is a lot of assumptions and generalization. So, based on literature, we know this waste contains this, and we could use it for A, B, and C. But I think, yeah, it's going to be a process. And I think we need some smarter people than me to figure it out as well.
Thank you. Are there other questions? Yes, we have one from, okay, I'll follow up with Margaret's. Is one idea we have had is to get our local authorities to act as a mediator for our industries. And we would love to create a network of recyclers across the country. So maybe that's one of the ways it could work. Yeah, perhaps that could work there in Copenhagen or Denmark as well.
Yeah, definitely.
So I guess, Margaret, from my perspective in South Africa, and maybe not just South Africa, there are many countries where there's an inherent distrust in your local authorities. So asking them to hold the space as the mediator may not work. But then I guess we have things like the Strategic Water Partnership Network, which can actually fulfill that role instead, where there's hostility towards the local authority. We also have a question from Hala, which says, I really enjoyed your talk. Just wondering how or if circularity could work as well in a vast country such as Canada, where I live, where distances between complementary industries may be huge.
So I think this is a problem that we're also experiencing in our current project that we're working on, which is primarily on acid mine drainage and using industrial waste that's co-located in acid mine producing regions to treat the acid mine drainage. And the first solution that we found is that the process needs to be modular so that we can change it from site to site. And it also does need to be tolerant of a few variabilities. One of the products that we're using to treat the AMD is a biomass source. And if you are in one area, such as an area with an abattoir, you could use the sludge, the organic rich sludge that you generate from the water treatment process. But if you are in an area that doesn't have abattoirs or anything like that, you could use whatever biomass is generated predominantly in that area. So we've seen studies like from Japan where they're using rice husks to treat the AMD, or there's some studies in South America where they're using banana peels. So it does mean there needs to be variability and modularity, which makes it difficult. But again, it might be something that needs to be streamlined and optimized and have this database of recyclers and waste producers and users so that we can facilitate that better.
And I guess also it's then doing a little bit of like LCA, life cycle assessment type of work to just to make sure that your life cycle impact is negative rather than like positive. What I mean by negative is it's diminishing rather than additional, to so that you do better than doing nothing as opposed to doing worse by doing something.
Exactly. Yeah.
Yeah. Cool. I'm not seeing other questions. Just going to look again. Okay. So there don't seem to be. If one comes up while I'm chatting, I will ask it. But then I would just like to say that next week, Monday, we have Simone doing the next lecture for us. So Sarah has said that she will drop messages in your inboxes. She just didn't want to spam everyone, which I'm very grateful and I appreciate. So expect that email. And then on Monday afternoon, Sarah, same time, then we will be listening to Simone Damsfeste and her presentation. Fantastic. Okay. Well, thank you all for tuning in and share the link with everyone. And thank you, Sasha, for a very nice presentation. It was great. And I'm very glad I didn't work at the abattoir. And as I said, please don't forget to register for the conference so that you can come and enjoy some sunshine with the rest of us. It's not fair that we hog it down here in the global south. You guys also from the global north need a bit. So chat to you soon and see you soon. Ciao, everyone.